Okay, this will be the last video of the course, section 5.5, projective transformations of conic sections. As I said at the beginning of this chapter, there is no difference between conic sections at the level of projective transformations. Let me explain that visually, and then we can have a look at how it works algebraically. So let's have a cone. So this will be my z direction, and then let's take this as an x direction, and this is a y direction. And so that my cone will just be this, version. X is given by the equation z squared is x squared plus y squared. So we get a circle of radius z as we go up the z coordinate. Now, if I embed this circle that I've just drawn here in the plane, which is where z is 1, then saying that z is 1 here gives me precisely a circle. So z is 1 implies that I get a circle. But of course we can, so this is indeed a projection of the cone, which, if you think about it, is composed of lines through the origin, so it makes sense as a projective object, and it's a projection of that projective object into onto a particular affine chart, which is given by z equals 1. So if we're looking at coordinates x, y, z, homogeneous coordinates x, y, z, we get a circle if we project onto the affine chart given with z as 1. Right, now what happens when we project onto the affine chart given by x is 1? Might be easier to just try and do a new cone here, and I'll just let that be my x equals 1 chart. So this is the point. This is x. Now it's the point 1. Then I'm going to get a shape that looks like this. So I'm going to be intersecting with this cone in a thing that looks like this, and indeed this is a hyperbola. So if I set x equals 1, I get a hyperbola. And if you don't believe that, well, let's just plug it in here. If I've got z squared is x squared plus y squared, and I put x equals 1, then I get z squared minus y squared is 1, which is the equation of a hyperbola. Now, if you want to get a parabola, you have to do something where you take a non-standard affine chart. So we need to take one where it's going to be parallel with the side of the cone. So I'll just draw it, and we'll see if we get the right result. So to be parallel with the side of the cone, I'm going to need x to be decreasing at the same rate that z is increasing, for example. So I need a plane parallel to the plane that's parallel to the side of the cone, and that will be where x is x plus z is equal to 1. So let's say that this is the line x plus z equals 1. And if I plug that into the equation x squared plus y squared equals z squared, then I get x squared plus y squared equals 1 minus z all squared, which gives me 1 minus 2x plus x squared. And if I cancel the x squareds, I get the equation y is equal to 1 minus 2x, which is a fairly clear just translation of the standard parabola that we're used to. Y squared is 2x. Well, I'm a reflection, but anyway, it is definitely the same shape as a parabola. Okay, so that's the visual picture there, and as we've seen, as we been making the point, the fundamental object here is not the thing that you get once you are projecting to an affine coordinate chart. It's the object that you start with, and in fact these are all related by projective transformations, because these planes that I'm drawing can all be moved one into the other one by a linear transformation of a three-dimensional space. So we can move any of these projections, so these affine charts. Oops, sorry. We can move any of these affine charts to another one through a projective transformation, i.e. a linear transformation of affine free space, right, which is the same as a projective transformation of two-dimensional projective space. I suppose I should say equivalent. What does one of them look like? Well, for example, we started off with the affine chart that you get by setting z equals to 1. So that's a plane. But if I want instead the affine chart where x is equal to 1, then here is a projective transformation that does it. Doesn't really matter what I do to y, so let's just leave y alone, like that. But I want to swap x and z, and I can do it if I use the that matrix. So that's going to swap the coordinates x and z, and so it's going to take one of these planes for another one. And it's not too difficult to see, once you've done that, that you can move you can rotate your plane so that it's pointing in a diagonal direction with the appropriate matrix. I would consider that to be a proof of the equivalence of all of these conic sections under projective transformations. But let's follow the notes and give the statement of what will be theorem 522, and it's the algebraic proof that is in there. Right. So theorem 522, for any conic section C inside A2, there is a projective transformation T which sends P2 to P2 such that C is this transformation, C is a transformed version of D restricted to the third affine chart. So that we're taking a thing starting in the third affine chart, so that C is TD restricted to this third affine chart. So we don't need to take cases, but we will. So we split into cases for each type of conic section. So let's start with the ellipse. So what we're going to do, right, so first of all, I should have just made the point here that where D is the circle. That we discussed above, that defined by z equals 1. Okay, so we're going to see that everything can be related back to the circle. Well, we've already done the ellipse. This was done in proposition 4.5. And we know that we can, any affine transformation, so in this third coordinate chart, can be done, can be turned into a projective transformation. You just take your affine transformation and fill it out to a projective one. So specifically, if the coordinates are UV, mapping to AU BV, then this will take the unit circle to the ellipse with equation x squared over a squared plus y squared over b squared is equal to 1. And how do we turn that into a projective transformation? Well, we can just decide that we're going to leave z alone. So take x, y, z to ax, by, z. It's the easiest way to do that. Right, what about a hyperbola? How do we transform a hyperbola to a unit circle or backwards? So we'll take a particular hyperbola. So let's C be the hyperbola 1 plus u squared over b squared minus v squared over b squared minus u squared over a squared is 0. And then define the projective transformation T, which sends x, y, z to ax, by, z, sorry, az, by, x is what we want, and then let's see what that does. So for a point P is equal to x, y, z in the unit circle, let TP be equal to x dashed, y dashed, z dashed. That is going to be related by this equation, so az, by, x. So in the third affine chart, we're going to have, so x is going to be equal to z dashed, y is going to be equal to y dashed over b, and z is going to be equal to x dashed over a. And then the point P in D satisfies x squared plus y squared minus is equal to z squared, so minus z squared equals 0, if and only if T of P satisfies, well, you just plug them in, you get 0 equals z dashed squared plus y dashed over b all squared minus x dashed over a all squared. So restricting to the third affine chart, we see that, so we're just going to have to divide this through by z dashed squared. So y dashed over z dashed over b all squared minus x dashed over z dashed over a all squared. but these are the coordinate functions that we get from u and v. So this is v squared over b squared minus u squared over a squared as required. I'm not going to go through the final description of the parabola. I'll leave that to you to have a look at. There won't be any value in me just writing down all the stuff in the notes. So for the parabola, refer to the notes and make sure that you understand how that is working. But it's basically the same idea. We just need a slightly more complicated version. Right, so let's just write down an easy corollary. 5, 2, 3. So any two conic sections are projectively equivalent. And well, the proof of that is just to say that, well, we know how to send everything to the circle. So if you want to send something to, you send one conic section to another, first of all send it to the circle, then send it to another one, and then just compose those two things. So if T is a projective transformation, and it corresponds to an invertible matrix operating on affine 3 space. So we can find its inverse, and so the inverse is also a projective transformation. So, and if T is invertible and M invertible, then we know that if you take the determinant of the two things multiplied together, then this is also invertible. And so take one thing to the circle, use the inverse to take it to the to your other thing, to your other. So say T sends C1 to D, M sends C2 to D, and then how do I get from C1 to C2? Well, I just do, first of all, I need to take T to D, and then I compose with M to the minus 1. That will take me from C1 to C2. And that gives me the equivalence of all of these things. So I've remarked 5.24 I've already done in the description that I've already given at the beginning of this subsection, so I won't go through that again, but I think one can see these things conceptually just by thinking about how planes are moved about through projective transformations. Thank you for taking Introduction to Geometry.